Chapter 5, slides 1 through 11. In this chapter, we're going to continue looking at molecular structure and add to the previous chapters that we've been studying about conformations. We have touched upon a little bit of structure. And again, this chapter has no chemistry in it. Okay, we're still just looking at a molecule and trying to understand something about it. So we're going to bring up a few terms here, the first being stereochemistry. And stereochemistry is really about the 3D nature of the molecule. And if you look in this example that I have down below, you'll see that I have a tetrahedral carbon that I'm focusing on. Right, there's this tetrahedral carbon. And if you look at the longest chain that I have right now, technically I have one carbon here, that's the carboxylic acid, and the second carbon is the tetrahedral one. And it looks like the same on the right-hand side. I got two carbons. And if you look, carbon 1 in both cases has a carboxylate group, CO2 minus. Carbon 2 has an R, an ammonium, an H3 plus, and a hydrogen. So these two molecules, as presented, have the same molecular formula, the same connectivity, everything's connected in the same way. But if you'll notice that the orientation through space around the tetrahedral carbon, number 2, is not in the same position. Thus, if we were trying to fit them into their boxes, into an area where they fit and conform to, you'd notice that on the left, everything works out with the hydrogen, ammonium, and carboxylate, right? Gray, blue, red, and they would fit perfectly into their little box. But if I just reorient them, the carboxylate would fit, but because the hydrogen and the ammonium were swapped in positions through space, they won't fit into their required boxes. And so you could understand from, say, a pharmaceutical point of view or even materials point of view that through space is actually going to make a huge difference in function. So the two molecules that you see here, their relationship is indeed isomeric. They are isomers, but they're not constitutional isomers. They're stereoisomers. And so we're going to discover the differences in different types of stereoisomers in this chapter. So let's review. A constitutional isomer has the same pieces, but different connectivity. And I have my Lego pieces here. It's like giving a kid the same pieces, but then, or you give two kids the same pieces and each kid goes into a room and puts them together differently. So they have completely different connectivities. An example that we would use might be something like butane. We could have butane, it's C, 4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. And then I could have 2-methyl propane. It's also C4, H10. But they're connected completely differently. They are very distinctively two different molecules. Stereoisomers, however, are the same connectivity. So they're the same pieces and the same connectivity, and their only differentiation is how they're put in space, connected through space. And handedness is a great way of thinking about it, and it's a word that we're going to use a derivation of the word handedness to describe some stereoisomers. An example might be our hands. That's why handedness is used, and I have a glove, a right-handed glove and a left-handed glove. You know that they have different functions, right? Very difficult to play baseball with a right-handed glove if you're trying to fit it onto your left hand, right? But all the connections are made. Here's the palm, here's the thumb, here's the palm, here's the thumb, followed by the first finger and the second finger and the third finger and your pinky, right? The same orientation or connectivity is made, but they're made in a different order, which makes it handed, right-handed or left-handed. Now, under the umbrella of stereoisomers. There are different types of stereoisomers. There are something called enantiomers and something called diastereomers. And these are relationship words. When you have two different molecules that are stereoisomers, they might be enantiomers. The relationship between the two might be enantiomers, or the relationship might be diastereomers. Okay, so we're going to talk about that and how to distinguish between these two types of stereoisomers in this chapter. First, let's just make sure we understand our constitutional isomers. These again are same molecular formula, but different sequence, totally different connectivity. And I've already covered the butane versus the 2-methylpropane in the previous slide. And here are some more with some heteroatoms. You might have C2H6O. You could put C2H6O together as an alcohol, or you could put the oxygen flanking on either side of it with the carbons and make it into an ether. Very different functionality, different connectivity, and so it's going to serve different roles when we are using them in chemistry. 1-propanol, again with an oxygen in there. You're putting the alcohol. See, we have the same functional group, alcohol, but different orientation. I could have put the alcohol at carbon 2 instead of being at carbon 1. So this is the alcohol at carbon 1. Here are the alcohols at carbon 2. I could have even made an ether with a methyl on one side and an ethyl on the other side. That's another constitutional isomer, completely different. But I just wanted to show you that you can try different functionality with the same molecular formula, or the same molecular formula, same functionality in the third case, but with different connectivity. So these are all constitutional isomer relationships for each row. Okay, so when you're given two molecules, the first thing to do is to see, are they constitutional isomers? That's the first thing you should do. Check their connectivity. Try naming them. If the naming is super off, right? 1-propanol versus 2-propanol, that's very different. So you can see very clear as day that those are constitutional isomers. When you get to stereoisomers, you'll notice that it'll have the relationships when you're comparing two molecules and asked, what's the relationship? First, check for constitutional isomers. If you'll notice for these all have C5, right? We've got the cyclobutane, that's 4, plus the methyl group, C5. How many hydrogens are we talking? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And an oxygen. So if you look for every single one of the molecules that I've drawn, they're all C5H10O. And they are all a cyclobutane. Longest parent chain is cyclobutane. And starting with the alcohol at 1, for every single one of these, the alcohol is at 1. The methyl is at 2. Even the one at the bottom right, the alcohol is at 1. Again, remember, you're the one that numbers. 1, 2, 3, 4, alcohol at 1, carbon at 2. So naming these right now, from what we know, there isn't going to be a difference between any of these other than some through space relationship. Now I'm going to tell you right now that the top two are diastereomers. The relationship between the middle two are enantiomers. And the relationship between the two drawn at the bottom, see if you can see it. Take one in your brain, flip it like a pancake, and try to overlay it. And if you do, what you'll see is that they're actually the same molecule. Okay, so what we're going to do in this chapter is start understanding how to look at the relationship between two molecules and understand whether they're diastereomers, whether they're enantiomers. Maybe it's tricky in the way that they are presented, like in this last case, and they're actually the same molecule but just drawn differently. It's really important to make sure that you understand and can validate the distinctions between isomers. And as you'll see in this chapter, why it's important to distinguish between diastereomers and enantiomers and what effect that has chemically. So we'll come back to that and learn how. You're not expected at this point to know how to distinguish between them. We need to learn a little bit more about relationships and the different types of stereoisomers in order to make those calls on relationships. So what we're going to do now, instead of talking about relationships, okay, I'm going to now focus on, say, one molecule. Okay, let's just look at a molecule. And let's talk about what makes a stereoisomer chiral or achiral. Okay, so what we're going to do is we're going to talk about how we're going to assess a molecule and whether or not it is handed. Meaning, if I swap around some groups through space, will it make a difference in the molecule, in another molecule, when I'm trying to relate it to something else? So to do this, we have to look at a molecule and determine whether it is handed or not, whether it has the opportunity to move its pieces around and be handed, meaning, oh, I moved the pieces around, it went from right-handed to left-handed, okay? So this is called chirality. And it's important to understand whether or not a molecule, just one molecule, is chiral or not. So if you look at this, I took a molecule and we're pretending that it's looking at itself in the mirror. So it's like going up to the mirror and touching itself, right? There it is. The hydrogen is right at the mirror, and then in the back, right, is the ethyl, and in the front is the methyl. So this is a mirror image. It's reflecting itself in the mirror. Okay, I've drawn a more ball and stick model off to the right here, and you can see if you took that molecule out of the mirror and you tried to overlay it, make it superimposable, you would see that there's no way to take, if this became its own molecule, and take that molecule out of the mirror and try to superimpose it, what you'd notice is that they won't overlay. Two of them will overlay, but the other two will be out of sync. Very similar to the first slide that I showed you. In this case, the relationship between these two molecules, the first molecule and its mirror image, are enantiomers. Okay, this is not practical. The word chiral means that that the other molecule that you're comparing it to is non-superimposable. Achiral means that the two molecules that you're looking at are superimposable. So when you take it, let's say the mirror image out, they overlay. So chirality is something that is very easy to define. It's when you have a molecule and another, and it has the ability to have handedness, like your right hand and your left hand. So when things are not superimposable, two molecules are not superimposable on each other, they're considered chiral. But when they are superimposable on each other, they're considered achiral. So that's all well and good when you're trying to, define these terms. But when you're talking about massive molecules, like really big molecules or compounds, this is not a very practical way to figure out if a molecule is chiral or not. I don't want to try to visually figure these things out, okay? So it's a very impractical way. Although it is the definition, it's an impractical way to decide whether a molecule has chirality. So kind of like dipole moments. Do you remember how in the previous chapters we talked about how dipole moments, there were two things you had to do to figure out a dipole moment? You had to consider the individual bonds to see if the individual bonds had polarity to them, and then you had to consider the overall geometry of the molecule. Well, chirality, we can sort of break down into a little equation like that too. We're going to look for one or more chiral centers. You don't know what those are yet, but we'll define those. And you're going to check that the molecule does not have a plane of internal symmetry. Yikes, what does this mean? Well, I've got the chirality equation up here at the top, and we're going to go through this point by point, okay? So the first thing we have to learn is what a chiral center is. And this is actually pretty easy to define, and this is going to help us a lot. A chiral center, and it's called many different things. It depends on which book you're using. They'll call them chiral centers, they'll call them stereocenters or stereogenic carbons or asymmetric carbons. These are all the same thing. Okay, so these are all the same term. Chiral center, stereocenter, stereogenic carbon, asymmetric carbon, that they're all talking about the same thing. So don't be too confused by all the lingo. It depends on which book you're using or which professor's talking. So a chiral center or stereocenter, I like to use the word stereocenter. I don't know why. I think you'll see me slip into stereocenter, is when you can identify an sp3 carbon. So you have to have a carbon that's sp3 hybridized, and it must be bonded to 4 completely different groups. And I say groups, not atoms. Okay? So right now you can see that this black carbon right here has tetrahedral sp3 orientation, right? So hybridized sp3, you can see the tetrahedral nature of it. And the 4 different groups are represented as different colored atoms at this point: red, orange, green, and purple. So that would be considered an asymmetric center or a stereocenter or a chiral center or a stereogenic carbon. Like I said, whichever one you need. So as long as you have one or more chiral centers, okay, that's the first check. We'll get to the internal plane of symmetry later on, but I want you to get used to identifying chiral centers. So let's take a look at some examples. In this first one, let's highlight all chiral centers or stereocenters. I'm going to number the carbons so we can make this task a little easier to follow along. And I want you to pay strict attention to carbon. Let's focus on carbon, okay? Carbon 1. If you'll notice, carbon 1 has 3 hydrogens. Carbon 1 is tetrahedral. It's sp3 hybridized, but it has 3 hydrogens, so it doesn't have 4 distinctly different groups off of it. Not a stereocenter. How about carbon 2? Carbon 2 has a methyl group on one side and this whole big group on the other. Looking promising. However, carbon 2 has 2 assumed hydrogens. So these are the same. Those 2 hydrogens are the same on carbon 2, so it doesn't have 4 distinctly different groups off of it. Same goes for carbon 3. Carbon 3 has 2 hydrogens off of it. And so those are the same. So again, it's sp3 hybridized, but it doesn't have 4 distinct different groups off of it. Let's look at carbon 4. Carbon 4 has this ethyl on one side, right? It's got carbon 5, carbon 6. Again, we're looking at groups, not atoms. It's got this ethyl group on one side. It's got this propyl group on the other side. It's got an OH group, and it has, hard to see, but an assumed hydrogen. Ooh, carbon 4 has 4 distinct different groups and is sp3 hybridized. So therefore, carbon 4 is a stereocenter. I found one. Carbon 5 has 2 hydrogens off of it, so that totally negates it from being a stereocenter. And carbon 6 also has repetitive groups off of it. So there's only one carbon that's bearing 4 distinctly different groups as an sp3 hybridized atom, and that's the blue carbon that I've highlighted. I'll skip the repetitive ones, but you can see hydrogens, hydrogens, the 2 assumed hydrogens at the carbon here make these carbons non-stereocenters. However, the carbon right here has a hydrogen, a bromine, an ethyl, and a methyl. 4 distinctly different groups off of it. That carbon is a stereocenter. Lastly, we can see, let's see here, hydrogens, negate that one. Hydrogens, hydrogens, hydrogens. Too many hydrogens of the similar group. 2 hydrogens, 2 hydrogens. So those carbons are not. What about this one? We've got methyl, methyl. Oh, nope. That one's not either. So that one's not. How about this one? You've got methyl, ethyl, hydrogen, and ooh, this crazy branched one. Definitely different. So that carbon is indeed a stereocenter. Take a look at the examples down below. In the examples down below, it looks like we might have hopes of a stereocenter. Hydrogen on the carbon, OH on the carbon, ethyl on the carbon, but oh, ethyl. That is a very symmetrical molecule with the same exact groups on either side. I'm going to add one here. Sometimes people will draw things like this. And I don't want you to think that just because there's a wedge, that it is a stereocenter. Sometimes people put wedges in and it's not a stereocenter. The carbon here looks like suspiciously like it could be a stereocenter, right? It's got the hydrogen, it's got the alcohol, it's tetrahedral. But if you look, I'm going to say carbon 1 to carbon 1 prime, carbon 2 to carbon 2 prime. So far, they seem to have the same flanking groups. And when they get to carbon 3 prime, and then they move in the other direction, there's no way of breaking that tie. Technically, those 2 groups in either direction are exactly the same. And this is not a stereocenter. Despite it having a wedge and despite it kind of looking like it might be a chiral center, it is not. And you can see that it's due to some symmetry as well. The molecule, just like the first one, is symmetric. And the symmetry is what makes that carbon not a chiral center because it has repeating groups on either side. Same goes for this carbon, repeating groups, methyl and methyl. It doesn't have distinctly different groups. Same for this last one. No carbon has 4 distinctly different groups. This one has a methyl and a methyl. This one has 2 hydrogens. This one has the same branched groups on either side with a methyl and a hydrogen. It's very symmetrical and repeating in all directions. Okay, so this is the first step in learning to figure out if a molecule is chiral or not. Now understand that all we've done is looked for stereocenters. Just because you have a stereocenter doesn't mean that you have chirality. Remember, this is just the first step in determining chirality for an overall molecule. Okay, so if I want to understand if a molecule can be handed, right, have a right hand and a left hand or some other stereoisomer, I have to figure out chirality first. I'm going to wait and talk about internal planes of symmetry in a minute. But chiral centers, right, you have to have one or more chiral centers. That's our first big step into determining the overall chirality of a molecule. Just because you have a stereocenter will not necessarily mean the molecule is chiral. So you need to get better at identifying those stereocenters or chiral centers. And I leave you with this practice slide for you guys to identify or highlight or put a star next to any carbons that you find are chiral centers. Okay, this brings up a little bit of a problem, as I mentioned before, right? When you guys are trying to figure out if the relationship between two molecules is constitutional isomers or stereoisomers, I hinted at the fact that naming the molecule might help, right? Take a look at these two superimposable molecules. They're actually the same molecule. And you can see that if you tried naming it, 1, 2, 3, 4, you would have 2-methyl, 2-bromo, butane. 2-methyl, 2-bromo should go before the methyl, 2-methyl, butane. And because the molecule can be superimposed, the other one in the mirror can be superimposed, it actually has the same name, 2-bromo, 2-methyl butane. They're the same molecule because they can be, you just have to take it out and bring it around and everything will overlay perfectly. That is not the case for this first example here. You'll notice that it is 1, 2, 3, 4. 1, 2, 3, 4. Now in this bottom case down here, notice that, using your skills from the previous slides, there are no stereocenters for the molecule. Therefore, they are superimposable. That's one of the checks. If you have a molecule and it does not have a stereocenter, then its mirror image is, you're going to be able to overlay the mirror image. So as I mentioned before, how impractical it is to try to look at a molecule and decide whether it can be overlaid or not. Well, the first thing you need to do is look for those stereocenters. If we don't see any stereocenters, then the molecule already fails the chirality test. No stereocenters, totally achiral. And that means that its mirror image must be superimposable on itself. Look at, we didn't even have to do the whole, in our heads is the mirror image superimposable. Like that's hard to do as the molecules get bigger. All we had to do was see that there were actually no stereocenters for the molecule. Fails the chirality test right there. I know it's achiral then. The A meaning not. It's not chiral. The first case, however, at carbon 2, if you notice, carbon 2 has a methyl group, it has a hydrogen, it has a bromine, it has an ethyl. So it has 4 distinctly different groups off of it. Therefore, that's a stereocenter. And without getting into internal planes of symmetry yet, I have a good bet that this molecule may be chiral. And when you actually, since this is a small enough molecule, I can look at its mirror image and then try to take it out of the mirror and overlay it. And what you'll find is that they're not superimposable. Therefore, these molecules are chiral. That means that there's a right-handed and a left-handed version for this molecule. But 2-bromobutane is all I got right now from IUPAC to name these, and I'm telling you that these are 2 different molecules. So how do we do that? Well, let's take a little bit of time and talk about how we can, when we have chirality, when we have 2 molecules that are not the same, they're stereoisomers, how do we name them so that we can distinguish between them?